All right, let's talk about L'Hopital's rule. Here's how that spells out. What L'Hopital's rule is about it's about another way of determining limits. You know, we talked about in our first calculus, we talked about different types of ways to get limits, from factoring to the multiplying by the conjugate of a radical expression. What else did we do? Oh, divide top and bottom by the largest power of x. If x was going to infinity, we could divide top and bottom, and that those all still apply. It's just now we are going to talk about another rule here that we can apply. Yeah, in solving limits, a lot of it is the type of form that you have. We didn't talk about a whole lot. We didn't talk a whole lot about forms of limits in Calculus 1, but it's really about indeterminate forms of limits. Spell that. And the two we start with here, two indeterminate forms. In other words, forms you can't tell right off the bat what they do. The two forms for L'Hopital's rule, indeterminate forms, are 0 over 0 and infinity over infinity. So in other words, if you plug in whatever x is going to, whether x is going to 1 or x is going to infinity, and you get 0 over 0 or infinity over infinity, those are what are known as indeterminate, meaning they could be 1, they could be 0, they could be 100, it could be infinity. You just can't tell, that's why it's indeterminate, okay? You just have to do some other stuff, and then hopefully you can determine what that limit does. Now, forms of limit that we know the limit of that are not indeterminate, the ones that we can determine, if we have, so forms of limit we know the value of, 1 over infinity, or any number over infinity, what does that go to? 0. That goes to 0. The good example is limit as x goes to infinity of 1 over x. We did that one, you know, way back when. Yeah, you got 1 over infinity. That goes to 0. But there are some other forms of limit that we know. 1 over 0. If we've got a limit that goes to 1 over 0, or, I mean, I'm using 1 here, but it could be any constant. 1 over 0. Well, a good example of that is this. So you got the limit as x goes to 0 from the right of 1 over x. There it is. X goes to 0 from the right of 1 over x. Well, if you look at that, what do you got? So 1 divided by a number that gets closer and closer to 0 from the right, positive.
Infinity.
That's going to be infinity. Now, it could be what else?
Negative.
If I approach 0 in a negative, that's going to be negative infinity. So anyway, depending on how it goes to 0, it may be infinity or negative infinity there. So those are just a couple of examples of ones we do know. So those aren't indeterminate. That goes to 0. This could go to infinity or minus infinity. You just have to see what the numbers do, but it's got to be one of the other of those. Okay. 0 over 0, infinity over infinity, those are indeterminate. Okay? Now, what do we do if we encounter one of those? Well, that's what we're going to talk about here. One example is, well, let me just show you. So say I've got the limit as x goes to 1, ln of x over x minus 1. Just to establish here what we're talking about. All right, so what we have is x going to 1. So if I plug in 1, ln of 1, what does that go to?
0.
That's 0. So the top goes to 0, and then the bottom, of course, 1 minus 1, that goes to 0. Hey, yeah, that's what we're talking about. This is an example of the 0 over 0 form. And so that's how we're recognizing these. We're just plugging in whatever x goes to and see. So that's the form of this particular limit. Now, we've encountered 0 over 0 before. We didn't maybe say it was 0 over 0, but before when we had 0 over 0, the denominator going to 0, remember what we did? We factored, or we used the conjugate, or we simplify. We can't do that thing. So anyway, this L'Hopital's rule, that'll give us a way to determine some other of these limits. So here's the statement of L'Hopital's rule. All right, suppose the limit as x approaches a of f of x over g of x suppose for limit you have the indeterminate form either 0 over 0 or infinity over infinity. Now what that says is you can only use this rule in those forms, with those forms. You can't use it for anything else. Whether, I mean, if it's not indeterminate, of course you wouldn't have to use anything else, but not all limits are 0 over 0, infinity over infinity. So this L'Hopital's rule only applies to those. Well, if it is one of those forms, then the limit as x approaches a of f of x over g of x, if it is those, that limit equals the limit as x approaches a of the derivative of x divided by the derivative of g of x, derivative of f of x divided by the derivative of g of x. In other words, what L'Hopital's rule says is if you've got 0 over 0, infinity over infinity, another technique you can use is just take the derivative of the top, derivative of the bottom, which, you know, a lot of times does simplify, not always, but a lot of times it does simplify things. Take the derivative of those and then see what happens to your limit. Okay? So it can be helpful. And that first one I talked about there is a good place for L'Hopital. So we've already said the limit as x approaches 1 of ln of x over x minus 1. That's 0 over 0 form. And so if we usually we denote when we do our L'Hopital, make a note of it there. So by L'Hopital, this means the limit is also equal to then the derivative. All right, so what's the derivative of our ln of x? 1 over x. And then the derivative of x minus 1 is just 1. So it's not quotient rule or anything. It's what we would hope the quotient rule would be, but you can actually do that in L'Hopital. Take the derivative of the top divided by the derivative of the bottom and see what that is, and that'll have the same limit. Well, hey, yeah, so now as x goes to 1, that goes to 1, doesn't it? because that, we can plug in x to be 1. So L'Hopital rule tells us we can do that. Okay. All right. Now, interesting here. Same expression, but let's run x goes to infinity. Maybe a little bit harder to tell the form of that one, but what have we got as far as form goes? If I plug in the infinity, ln of infinity divided by infinity minus 1. Okay, so that's not a value, but infinity minus 1 is infinity. Yeah, if you subtract 1 from infinity, you're still infinity. Now, ln of infinity, what does that mean? Ln of a larger and larger number. Sometimes it's helpful to think about the graph. If I just think about the graph of y equals ln of x, which looks like this, as we go out, as x goes out to infinity, this never flattens out, it never peaks out, it just keeps going up. So the ln of infinity is infinity. Yeah. So this form right here is infinity over infinity. Can I apply L'Hopital? Yeah, L'Hopital you can apply to infinity over infinity. So we can do the same thing, and we get, we already know it's 1 over x over 1. All right, but now what happens? As x goes to infinity, what does that go to?
0.
0, why?
1 over x is 0.
Yeah, you got 1 over infinity, right? Essentially you got 1 over infinity, and we just talked about that. 1 over infinity goes to 0. You don't have to write necessarily that, but yeah, 1 over infinity is not indeterminate, it's 0. It's always going to be 1 over something that gets larger and larger. Okay? All right. Yeah, I better mention, limit as x approaches 1, 4x minus 3 over x minus 1. Okay. The problem here is, can we apply L'Hopital? No. Now the form here I've got is 1 over 0. That's my form, isn't it? The top goes to 1, the bottom goes to 0. If I plug in x to be 1. Yeah, that's not L'Hopital. Not L'Hopitalable. Okay, because only time you can apply L'Hopital is 0 over 0, infinity over infinity. Because if I applied L'Hopital, I'd get 4 over 1, which is 4. And that isn't right. Actually, here, if you think about a table of values, or look at the graph of this, what you'll see at 1, you'll see a vertical asymptote. Maybe I should graph it before I make it right. If we graph this thing, just to kind of give us, I mean, this isn't proving it, but we could do it with a table or something like that. I think we get, that does not exist because one goes one way and one goes the other. Yeah. Okay. So it kind of does this at 1. So as we approach 1, one side goes to negative infinity, the other goes to positive infinity. This does not exist, you see. If we did L'Hopital, though, it would tell us it's 4. So that's what we're saying. You can't apply it unless it's 0 over 0, infinity over infinity. So you see what I'm saying? Okay. here's something else interesting. Limit as x approaches 0 of x minus sine of x over x cubed. Well, plug in 0, you got 0 minus sine of 0, 0. Top is 0. Of course, the bottom is 0. So we do have the correct form. L'Hopital. See if that helps. So L'Hopital here. That'll be the limit as x approaches 0 of, so what do we do? Derivative? What's the derivative of the top? Derivative of x is 1. Derivative of minus sine of x minus cosine x. Derivative of the bottom, 3x squared. Well, what happens interestingly up here is, what now do I have? 0, 0 still, don't I? 1 minus cosine of 0, cosine of 0 is 1, so 1 minus 1, that's 0. X goes to 0, so that's 0. I still got a 0 over 0 form. Well, guess what? If it's still 0 over 0, guess what we can do? We can L'Hopital again. So that's limit as x approaches 0. Derivative of 1 is 0. Derivative of minus cosine of x, positive sine of x, over 6x. Zero over 0 again. Yeah, so this could go indefinitely. I mean, it won't, but we can L'Hopital again. That'll be the limit as x approaches 0. Luckily, these aren't hard derivatives, right? That'll be cosine of x over 6. Hey, I think we're in business now, aren't we? Yeah, do the derivative of the top, derivative of the bottom. What do we got now? 1 over 6. Yeah, cosine of 0 is 1. All right. So that's what we're saying. 0 over 0 is indeterminate, because 0 over 0 here is 1/6. You just can't tell what 0 over 0 is going to be. Could be 0, could be.
So is there going to be multiple questions where you're going to have to do that multiple times? Over and over?
Yeah, yeah, I'm sure there's several of those in your homework, yes.
Okay. How many are we expecting? Like 8 of them? Like
I don't know. I can tell you that.
How many of them are going to be much more difficult than that?
I mean, if the derivative, sometimes the derivative is a little more complicated, so that's where the complication usually arises, is that derivative. Because you might have product rule, quotient rule.
yeah.
We'll do a couple more here.
Okay.
You kind of see what happens, but yeah, you could run into all sorts of things. All right, this one's not too bad. Limit as x approaches infinity. There's another infinity over infinity, isn't it? Yeah, it's infinity over infinity. Infinity squared, that's infinity. E to the infinity, e to a larger and larger power, that's going to get larger and larger. Yeah, that's infinity over infinity. So that's L'Hopital, which makes it limit as x approaches infinity, 2x over e to the x. Right, derivative of x squared is 2x. Derivative of e to the x is e to the x. Well, look at that. Infinity over infinity again, isn't it?
Yeah.
So let's do it one more time. I think we're just going to have to do it one more time, because that's going to be 2 over e to the x. Now what do we got? 2 over infinity. Yeah, so that's why I mentioned those other forms before. 2 over infinity is not indeterminate. 2 over infinity, that's 0, isn't it? Yeah, you got 2 divided by a larger and larger number. 2 hundredths, 2 thousandths, 2 to e to the 100, 2 e to the 1,000. That's getting closer and closer to 0. All right. Now, there's also a couple of other indeterminate forms, and that's what we're going to talk about next. But before we do that, let me get you to look at something else. let's talk about this. If I have two functions multiplied together, might seem kind of strange, but sometimes what we can do is we can rearrange that and make that appear different. It's the same, but there's a reason why we might want to do that. But anyway, f times g is equal to f divided by 1 over g. And the way you can see that is, f divided by 1 over g means f times the reciprocal. So that's the same thing. Now you might be saying, why in the world would I want to do that? But the point is you can, and there is a reason we want to do that in some cases. Now, the other thing is you can go the other way, g times divided by 1 over f. And the reason this comes up is because what this sets up, so this is a product, this is a quotient. And L'Hopital you need 0 over 0, you need a quotient. And so that's what this is going to set up. It sets up a way to turn it into something we can L'Hopital. Use a L'Hopital with one. All right. Because there is an indeterminate form that's a product. It turns out 0 times infinity is another indeterminate form. Zero times infinity is indeterminate. It's indeterminate. You just don't know what it can do. It may be 0. It may be infinity. It may be a number. Okay, that's what we're saying. It's indeterminate. You just can't tell if you have 0 times infinity what it is. Take a look at this. So the limit as x approaches 0 from the right of x times ln of x. Well, obviously x goes to 0, so that's 0. What happens to the ln of x as it approaches 0 from the right? Well, again, that's where you might want to look at your graph of ln of x. Yeah, ln of x goes to negative infinity as you approach 0. And so, like I was saying, this is indeterminate, and I'll show you that it can be lots of different things, so you just don't know what that does. Okay, that's indeterminate. 0 times infinity or 0 times negative infinity, same thing. All right, so what do? Well, if you have that indeterminate form, 0 times infinity, we're going to apply one of these conversions, if you will. You either write f times 1 over g, or f divided by 1 over g, or g divided by 1 over f. Do that to one of the, convert it to one of those forms. And again, like I said, that's going to set it up probably for your L'Hopital, if you have this indeterminate form, okay? So if you get this, then use one of those. Now the question is, which one do we want to do? And I think, judging here, if this is f, this is g, I'm probably going to leave g on top, because it's a little more complicated, you see what I'm saying? So let's write it as limit as x approaches 0 from the right, and do g divided by 1 over f. Okay, that's not too bad. See what I did there? So I did g divided by 1 over f. It's the same if you multiplied it, divide it all out. All right, well look at that. Now what form do I have? That's negative infinity. 1 divided by 0. Have we talked about what happened? 1 divided by 0 goes to infinity, yeah. This is a minus infinity over infinity, which, I guess we've had a minus infinity over infinity, but it is, it's L'Hopital. You can L'Hopital that. So this form now, we can L'Hopital. Use L'Hopital. limit as x approaches 0 from the right. So derivative of the top is 1 over x. What's the derivative of that? We'll probably think of 1 over x as x to minus 1. So the derivative would be minus 1 x to minus 2. Which, yeah, so this is the kind of thing you can maybe run into. We can go ahead and simplify that. So just some simplifying here. 1 over x, and that would be minus 1 over x squared, which is 1 over x times negative x squared over 1. See what I did there? Do the reciprocal, multiply by the reciprocal. Yeah, what does that simplify to? Minus x. Minus x. So that cancels into that, leaves me an x. It's minus x.
0.
That's 0. Okay. Like I said, 0 times infinity could be 0. Not always. Let's look at it up. This is a good example. Limit as x approaches 0, x times cotangent of 2x. Well, obviously x goes to 0, so that's 0. Times cotangent as x approaches 0. Cotangent of 2x. Well, cotangent of 0, isn't that one of the asymptotes of cotangent?
Yeah.
Yeah, can't divide by 0, so. Yeah, so that's, I might have to say this on the right or whatever, but just to make it infinity, the other side goes negative. Anyway, it's 0 times infinity. Okay, well this one, turns out it works out by leaving, actually, putting the cotangent 1 over the cotangent. So let's leave it, let's do this one. So do f, leave the f, and then do 1 over g here. And the reason this works out is because that,
It's 1 over tangent 2.
yeah, that's x over, 1 over cotangent is tangent. That's tangent to 2x. So I guess we could have thought about that, done that anyway, but, okay? Which works out to be, that's 0, and tangent of 0 is 0. That's 0 over 0. That's what we taught. Limit as x approaches 0 from the right. 1. Derivative of x is 1. Derivative of tangent of 2x. Derivative of tangent secant squared 2x, but then you need to multiply by the derivative of the inside, 2. So you get 2 secant squared 2x. Is that okay? And what is, so we got secant squared is 0, basically what we need to figure out there. It's what's secant squared is 0? Well, secant is the reciprocal of cosine. 1 over cosine?
So 1.
Yeah. Secant squared of 0, for secant of 0 is 1. So this is 1 over 2 times 1. Okay. So there's your proof. 0 times infinity doesn't have to be 0. It could be a half. And it might be infinity. It might be some other bigger number. You just don't know. It's indeterminate. You just have to work out, and this is one way to do it. Okay?